Should I get started?
Just go ahead and get started, and
People will file in. All right. Yeah. So so I'm gonna be talking about detecting photon rings with VLBI. This is gonna be kind of a fun experience for me because I have been on a few big paper or two largest, or I guess papers that have caused a lot of discussion lately, led by Avery Broderick. Big papers, a lot of discussion led by Avery Broderick, where there was a claim of a detection of a photon ring with VLBI. I have also recently published a paper in Galaxy Special Issues that will be part of the focus of this talk, saying that you can't do that with the EHT for various reasons that I'll get into. So feel free to grill me on my opinions on both of these things. Okay, so first thing is I'm guessing this is a foundation seminar, so some of you have some experience with what the photon ring is, but what this basically comes down to is that around any optically thin accretion flow around a black hole, you kind of get this natural ordering of structures in the image. So any image of an accretion flow kind of can be broken down into some subcomponents, and the subcomponents are indexed by the number of times a photon takes a half orbit around the black hole. So the first image you have is the n=0 image, and this kind of just corresponds to the direct image of the accretion disk around the black hole itself. So light just goes from the accretion disk basically straight just into your eye. After that, you kind of get this you get this n=1 image, and this is photons that have done a half orbit around the black hole and take it and go into your eye. And because of strong lensing in the vicinity, you get this demagnification. So this entire image kind of just gets squished into this thin and narrow annulus. And then you can go indexing higher and higher. So n=2 is a full orbit. And each time you get this little extra demagnification factor. So the ring becomes a little bit thinner and exponentially, or it gets exponentially decreasing in width and flux. And so kind of the goal of this talk is to figure out a way to use some sort of telescope like the EHT to get this guy, n=1. n=2 is really thin, really dim. This is going to be basically impossible, but maybe there is some hope that you can grab this n=1. And so to do this, photon ring. Why might be interested in doing this? Well, photon ring is, like I said, it's a key prediction from GR, and it also is kind of probes gravity near the event horizon, and it has this like universal structure for Kerr-like black holes. And then on top of this, the structure of this photon ring actually encodes a lot of information about gravity, about the spin of the black hole, the mass, and maybe inclination as well. So if we were able to measure the photon ring and its shape, we might be able to get constraints on basically the fundamental properties of the black hole. To do this, I'm going to be looking at my favorite thing, because I'm an EHT member, the Event Horizon Telescope. So the Event Horizon Telescope is something called a very long baseline interferometer. Basically how this works is you put a bunch of telescopes around the planet.
I have a quick, slightly dumb question. You go back to the photon ring. So if there's a departure from circularity, right, could it also be because, is that degenerate with having a very close binary? Like how close does a second black hole need to be, like, for this to be like a circumbinary?
That's a good question. I think people like Prashant probably have a better understanding of this than me, but I would expect that what is going to be more important is the mass ratio. So if they're similar in mass and stuff, then you're going to start to see some modification of the photon ring. If you have some really small black hole next to something like
mass binaries.
Yeah, equal mass binaries, then it's going to be I don't know, probably within a few m of the photon ring you'd start to see massive deviations, but I don't know off the top of my head this kind of stuff. This is pretty different from what I look at.
I don't think that's been done.
Yeah, okay. Okay, yeah, the only thing I know of is Jordy. Yeah.
I think usually equal mass. Right, yeah, exactly. And also I don't think they work out the demagnification factor, because also dynamical space time and all those things.
Yeah.
It's not straightforward.
It's not straightforward, but it could be confounding.
Yeah, also there's a way sort of to do it. We don't do it
Okay.
with face space and stuff. We
Yeah, let's start off. with-
Oh, yeah, with some of the face-based holography
Yeah.
stuff, that'd be fun. Okay. So my line of attack here is we're gonna assume it's a single black hole, M87, event horizon telescope, very long baseline interferometer. So we have a bunch of telescopes across the planet. And what they measure is basically phase delays between two telescopes on opposite sides of the planet. They correlate these signals and math happens, Van Zerdeke, whatever theorem clicks in, and what actually ends up popping out of this correlator are basically approximately the Fourier components, or as radio astronomers call them, complex visibilities. And so what this actually means is that the EHT, when it takes its data, it's not actually making an image. It's not like JWST where out comes this beautiful image of some galaxies. I'm sure lots of details with that. But we actually have a very different problem. We're trying to move from this Fourier transform to an actual image itself. And so what we're trying to really do is, do we have a shot at potentially measuring this n=1 photon ring? Well, so here are the visibility amplitudes, or the amplitudes of those Fourier components. And what you can see is I've kind of split this down into n=0 + 1, which is these solid lines, the n=1 emission, which are these dashed lines, and then the n=0 emission, which are the dotted lines. And what you can kind of see here is that they're very short baselines are, of course, dominated by this bright, puffy n=0 emission. And then what happens is we start getting to longer and longer baselines, this thin ring component here starts to have a lot of power on these small scales. And so you start to see that the n=1 emission starts to become much more similar to the n=0. But at the EHT limit, we're roughly at like something like 10% or a fraction of a bit. And so what you want to know is, can we do some like kind of clever modeling or some other data analysis tricks to actually extract this signal from the data? Because it is there. It's just a question of, can we actually reliably recover this? And part of this problem is now that because the EHT is this very sparse interferometer, so we don't just measure Fourier samples, we measure a handful of Fourier samples. So we only have 7 telescopes. I think radio astronomers look at this coverage traditionally and go, this is bad. But this is what we have to deal with. And the problem with this is that because we have such a sparse coverage, what the image on the sky we look at isn't just this crisp image, it's actually blurred, or it's actually like a blurred or a fuzzy version of it. So this is like we only have a few resolution elements. And then on top of that, because we have all these coverage gaps, I don't know, I don't dream in Fourier space or something, so I don't actually know what this would look like. I can't go from looking at Fourier amplitudes to an actual image. So instead, we have to use an analysis pipeline. And I think this is a little more new blood for the LBI or whatever, but I'm a big proponent of solving these types of imaging problems through Bayesian inference. And I don't know what the background of Bayesian inference in this group is, so I'm going to try to do a pretty rapid introduction to this. So the starting point of any Bayes problem is really picking your model or your prior. I use these two words interchangeably because they really are the same thing. Your model is a prior. So picking your prior and your parameters is related to just the model you pick itself. So we pick some prior. So this is something that we think encodes what we think the image on the sky is going to look like, whether this is an accretion flow, some image model where you force things to be smooth or sparse or some combination thereof. Once you have that, the telescope starts to kick in and you have something that you call your measurement model. And so what this measurement model does, it says that each image, it kind of gives you what the data probability distribution looks like. So for a given image I, there will be some distribution of data here, some distribution here and here and here. And then what you do is you multiply these two probability distributions together and you get your joint probability distribution. So you get your joint image, and this is really what you construct when you're doing your Bayesian modeling kind of structure. You're forming this joint probability distribution, which is your measurement model, that green thing, times your image prior model. What data then ends up being is a slice through this. So your measurement, what it does is it just picks a chord through this joint probability distribution. And so by picking a chord, you then form your image posterior. And so moving the probability of your image given the data that you actually see. Now, I say just picking a chord. I spent a lot of time in my PhD figuring out how to do this. This is computationally extremely difficult. There's a lot of literature on this. This is basically the foundation of most computational Bayesian statistics, but for our intents and purposes, it's a simple chord. So then the big problem, or the big thing that you have to worry about with Bayesian inference, is how you pick this. This depends a lot on domain knowledge, what a scientist thinks the thing should look like, and even the problem you're trying to solve. So the problem I'm trying to solve maybe enforces me picking a different image or a different model than maybe I would if I'm trying to solve a separate problem. And related to this choice of image model is really kind of a balance between the effective number of model parameters you want to fit and how agnostic you want to be, or how I want to be I don't want to assume much, or do I want to assume everything? So kind of at the bottom here, I have this on this agnosticism plot, I've got small number of parameters and very not agnostic. And I view this as something like a semi-analytic accretion model. So here I'm picking a really simple accretion model around a black hole, some geometric structure. Daniel has done a lot of work on this. It's really, really interesting. But you're assuming a lot here. I'm assuming GR, I'm assuming some specific space-time structure, I'm assuming some radiative transfer model. I'm building in a lot of physics into this. The next step up, a little less agnostic in the sense that I'm not building in explicitly GR into the model, maybe something like really simple geometric models. So fitting your model or your image with something like a ring, Gaussians, or some other blobby structure that you control. You're still making pretty strong assumptions. Like here, I'm assuming that there's a ring in the image and that there's additional flux, but it's not fully building in physics. On the other hand, you have these, what we typically call imaging models, which I tend to think of as non-parametric models of the data. So you try to assume very little. These things are very agnostic, but because of this agnosticism, you're paying the price, but you're gonna have to fit a lot of parameters to this. And kind of the focus of this talk is in the thing that I think caused a lot of controversy or whatever is.
Models are smoothed, right? They're smooth models, they're from the data smoothed.
They can be. So clean kind of takes that approach, but RML and these Bayesian methods don't so much. You can break down the image either into a discrete grid, and then you fit each pixel by pixel thing, or you could, the Resolve team, this is like a team up at in Germany, what they actually do is they really do fit a continuous model. They fit basically a really high dimensional Gaussian process, which is inherently something smooth and continuous. And then to make it computationally tractable, they'll discretize it, but discretize it on really small scales.
The reason I ask is we do very similar things when we do lensing mass reconstructions, right?
Yeah.
That matter.
Yeah. I think it's actually a really similar problem where you're trying to infer what the thing looks like after the instrument, and the instrument in this case is your galaxy. Yeah. So what I'm going to kind of look at is kind of bridging the gap here. So medium agnosticism, medium effective number of model parameters, and the point of this is that to maybe extract a little more physics.
Yeah, exactly. So that's my question. Is there, for example, if we're able to list out all the types of semi-analytic models or different, say, non-GR, things like that, is there a clear benefit to be, if you were able to enumerate all that, is there a benefit to doing that versus something that has other model parameters like imaging models?
Yeah. So I think, yes, I think there is a benefit to putting in a little more physics. One, it sharpens what you're trying to extract. So for instance, measuring it, going from an image to a spin of a black hole or a mass of a black hole is hard. It's really, really hard. Like most of the papers that we do is actually not just fitting the data. It's figuring out how to go from whatever we fit to actually what we care about. If you use these more physically inspired models, a lot of the time you're going to get direct parameter inferences of what you want. The downside is that I do have to assume. So I kind of view it as, what are you trying to do? In some sense, discovery, you kind of want to be agnostic. You don't want to assume that thing is actually in the image. So I tend to go for a discovery type thing. I think of being quite agnostic. And then when it comes to actually measuring, once you're kind of convinced the thing is there, and it actually comes to I want to measure what the spin of the black hole is, building in some physics makes a lot more sense there. Yeah. At least this has always been my viewpoint. They all work together, but yeah. Yeah.
Clarify, so when you say the choice of image model here, the choice for the purpose of inferring things about parameters or the photon ring or.
Yeah.
Okay.
Yeah. This is basically, yeah. What I mean is this is another good point. Whatever inferences you want to derive are going to be you're going to pretty much inform what the model you want to actually pick at the end of the day is. If I just want to get an image on the sky and don't want to worry about any of the physics that generated the image, an imaging model is pretty good. If I want to know if there's a photon ring, you need a little bit more, unless you want to put like Alma in space or something and get to the scale.
That sounds great.
Yeah, it's been brought up. So the goal here is to kind of construct this hybrid approach of this photon ring image model. So we're going to start with our image, and again, we can split it up into n equals 0. And here we have to focus on n equals 0 is quite complicated. It's heavily impacted by accretion turbulence, what's happening around in the accretion flow. So figuring out a good a priori model for this is difficult because your model is going to have to be really flexible. I don't know what this is going to look like from snapshot to snapshot. I have a very poor understanding. Maybe GRMHD people could tell me. I am not a GRMHD person, unfortunately. But so you want a pretty flexible prior model to this. On the other hand, this n equals 1 image, GR is really great. And anyone who's done GR, there's like no free parameters in the model. Once you just set what maybe the cosmological constant is and what G is, the model's basically like, GR is like, all right, we're good. I can do the rest, which is rather cool. But so because of this, the image, the model you need to do this n equals 1 ring can be quite simple. It's going to have to be a ring-like type thing, especially for the inclination of M87. We also know it's going to be quite thin, and we have an idea of what the rough scale is going to be. And so because of all of this, we can kind of break this model component to kind of deal with this flexibility. So what we'll do is we'll try to target the n equals 0 emission with this raster or image-based model. So we'll fit this like low dimensional pixels, like 5 by 5 grid of pixels to the data. And this will hopefully focus on this. Then on top of that, you can fit something like a thin ring model. So we'll put a ring model down that's going to be thin with the goal of like just targeting this. Now, I want to emphasize, this is a nice story and everything, and sounds good and it makes sense, but it just because you have this breakdown doesn't guarantee you're actually going to get this. It's quite difficult. I'll get into a little bit of this difficulty later, but if you do take this model as a given and you apply it, you can, all right, fill in this gap. You get these results from the broader 2022 paper called Photon Ring and M87, which I'm a co-author of, which is a fun feeling for me. But and so what you see is you have your thin ring model here, kind of consistent between each day, and then you have your raster here kind of soaking up this like so-called diffuse flux throughout it. You can see some trends throughout the days. This diffuse flux tends to live in this region here on each day. The ring looks roughly about the same size. So I think a priori, when you first see these results, or at least when I first saw these results, they look pretty encouraging. You're like, oh, this looks good. Maybe the model's doing what you want to. And a lot of the confidence in this paper was built up on an earlier paper in 2020. So this is a broader 2020 hybrid imaging and modeling VLBI interferometers. And so what they did in this paper is they have 5 GRMHD simulations. These are grabbed from the original EHT papers on M87. And we did this exact breakdown. So we fit this with our 5 by 5 raster and started looking at the ring parameters. And so when we did this, you can see the blue profile, the blue line here is the true GRMHD profile. The solid black line, which I think is probably one of the more important lines in here, is the estimated n equals 1 photon ring radius from these images. And then the green is the posterior of the ring parameters. And what you can see is that, like, I would say in like 4 out of 5, this one's a little dodgy cases, you actually do see that where the posterior lines up pretty well with where the photon ring radius is. And so that's pretty encouraging. However, one of the weird things when we did this fitting, really weird things that I don't think we have some explanation for, but maybe it's not as detailed as it could be, is that the flux ratio that we find in this photon ring is substantially too high than what you would a priori guess. I think Daniel, a lot of other people have done estimates for what you would roughly expect this n=1 photon ring flux to be. And when you're getting up into the 0.4s, the 0.5s, and the 0.6s, they're like 40 to 60%. That's high. It's really high. This is like a factor of 2 or 3 higher than the true.
So for Schwarzschild, we should be around 4% as well.
Yeah.
-5.
Well, it depends a lot on the magnetic field structure, I think.
Nice.
Yeah. So the magnetic field structure will impact this a lot for how bright the ring is.
And this can go up to 10%, 20%.
Well, sorry, so the 10%, 20% number, this comes from a stationary flow
Okay.
with isotropic emission. And it turns out the fact that you don't have stationary flows, you have Doppler factors that will differ significantly in the direct and indirect, in addition to K cross B factors from synchrotron, means that if I have full freedom, I can choose any sub-image ratio I want. In maths, it turns out this is usually between 10 and 20%, but there are instantaneous excursions from this, of course, as you go through the movie, where it can get quite high, even to sort of 40% level, but that's like a very rare event. Typically, that number is more.
Yeah. And we also know what the truth is here.
Yeah.
I can tell you, they're not. These are like a factor of 2 or 3 too high. And so the thing about this is I think Avery or Avery Broderick, the person who wrote this paper, and I have a different opinion on this than me, but what this does suggest is that this ring flux suggests that this thin ring is also modeling some of the n=0 component. Some of this n=0 ring stuff is bleeding into this. Yeah, right. There's no way the model actually can isolate these things, especially at the EHT scales we have, where it's quite dirty, like this separation. And so this suggests that there is some stuff being biased in, and then it becomes a question of, well, okay, maybe the radius isn't biased too much. We can trust the radius, but we can't trust the flux. And so to kind of go into this a little bit, this kind of starts a discussion of what we mean by detection and what we mean by measurement. And Avery in the 2020 paper claimed a detection, or at least it was worded in a way that claimed a detection. I think I don't really buy that language, mostly because I think to claim a detection, you need to meet a bunch of pretty high thresholds. I don't think the original paper did. So one thing is if I'm able to detect it, I have to be able to also detect the non-existence. So I want to know, maybe GR is wrong, maybe something happened, maybe the accretion flow is optically thick, and the n=1 photon ring is gone. I want to be able to have my model say there is no photon ring here. And so one of the tests you might want to do is, let's do a GRMHD test where there's no photon ring and see if what that thin ring component does. You also want to, in your detections criteria, not assume critical properties. One of the defining properties of a photon ring is that it's thin. Assuming that your model is thin, maybe bleeding over that edge a little bit, you're kind of assuming the answer that you're looking for. And then the other thing is, for detection, I think beyond just these things, is you kind of want these properties to correspond to theoretical predictions, right? It wasn't enough when CERN saw the bump. They're like, we see a bump. This is great. It's probably Higgs. Now we need to make sure that the decay patterns, all these other things actually match what the standard model says it is. And if any of those fail, then you're going, well, what the heck is this thing? It's not the Higgs as the standard model may predict. And so similarly for the photon ring, you want to make sure the photon ring diameter is something you would roughly expect. Its width is what you would roughly expect. The ellipticity is fine. You want it to be stable over time. The photon ring is kind of consistent over time, and it's largely achromatic. So you want this to really be in there when I would claim a detection. Now, this is this is a thing that I think is a little individual to the person, and maybe I think as a community we need to figure out a little bit more, but this is my view on it. On the other hand, I view measurements as very different. If a measurement is like, I'm going to assume the model is there, I'm going to start fitting things and see what we can extract. And then it comes a question of how reliable are my measurements actually. And so, you want to you might be like pull in certain things, like I'm going to assume there's a thin ring in the image. I'm going to assume there's some rough range for the n equals 0 and n equals 1 flux I want to build into my model. And you can build some of these things in. And what you may end up with is something like a hybrid imaging where you have a cascade of parameters where some are easy to fit. So things like the ring size, maybe that's the easiest thing to fit given your data. And then the next is the flux, the next is the width, blah, blah, blah. And you start going down and down until you get to this like regime where you have enough data that everything is measurable. But I think what I struggled with the original Broderick paper is, all right, I don't think it's a detection. Is it a reliable like measurement device, or can it make accurate predictions of what's actually?
Another way of saying what I think we think of this is that we, in the Broderick et al. Paper, the attempt was to avoid false negatives.
Yeah.
And the danger is that we could easily have false positives. Saying we could have false positives is sort of a contrapositive way of saying what you were saying before when you said in the detection, in the Broderick paper, we sort of assuming.
Yeah,
it's
yeah,
there
exactly.
And then trying to pick out something.
Yeah, exactly. I think that's exactly right. What you said, Peter. Quite eloquent. Thank you. Okay.
Well, I had a question.
Yeah.
So when we define magnification, typically we use ratio of widths.
Yeah.
Right? So when you look at fluxes and widths, shouldn't there be some sort of sanity check that you can make?
Yeah, exactly. You could do something like that. I think this is included in the type of thing. Like you would want to do like, like Michael's Lyapunov type thing or whatever you want to do.
Yeah.
Some like maybe approx. How well that does for n equals 1 is, but you probably put some bounds on it. And at that point, you would want to make sure.
So what I was wondering specifically was, you showed how the flux ratios are like overshooting.
Yeah.
To do that for the widths, would you get some numbers and then say that, okay, those look okay and it's.
Yeah, I think you could try something like that. Yeah, I think that's a good idea to try to look at something like that. Okay, so I think so the result of this is that I think Peter, myself, Michael Johnson, Daniel, Dom, a lot of us kind of wanted to analyze this. What is hybrid imaging actually measured? So what I think is the broader 2020 and 2022 results are mixed. The radius seems like it might be all right. The ring flux is obviously wrong. And so the question is this ring flux actually robust, or the ring diameter more robust and easier to measure? Can we accurately get this in all these simulations? And so to do this, the first thing we did is we looked at a GRMHD simulation and decomposed it. So we looked at a data set that was just n equals 1 emission, a data set that's just n equals 0, and then a data set that's n equals 0 and n equals 1. This will kind of let us see what each model is keying in on when there's only one of these components relevant. And so to each simulated data set, we fit two models, this raster plus thin ring model. This is very similar to the Broderick et al. Model. And then as well, a raster plus a thick ring model. And by thick ring, I just mean I don't force the ring thickness to be 1 microarcsecond. I let it be a free parameter and see what the data wants it to be. And so when we did this, we've got some pretty interesting results. So I would say for n equals 1, it was like a pretty reasonably good success. We get that you don't want any raster flux, so all the flux is dumped into this thin ring, or like most of it's dumped into this thin ring. The width is like, maybe there's bias high. This is likely just because we just don't have long baseline coverage, but there's at least support down at the truth, and the radius is, or the diameter of the ring looks really good. Now, something interesting happens when we go to n equals 0. When we look at n equals 0, it still wants this ring. It always wants this ring. And this actually makes sense from in a certain regard, where this image is dominated by a ring. So what's it going to do when you put a ring on it? It's going to try to fit the ring with whatever ring-like component you have in the model. So what you see is you have this ring, it has a diameter. The diameter looks, reasonably good with what you would expect for n equals 1, this black dashed line, but posterior is quite broad. It's also consistent with n equals 0, so it's unclear what it's focusing on. But again, you see this flux is huge. And it is not really tracking either n equals 0 or n equals 1. It's some weird combination of it. And then when you look at the n equals 0 plus n equals 1, you get a very similar story. It looks largely similar to just this n equals 0 emission, I would say. And so this is also kind of unclear, but what it does fail is it does fail that detection test, like what I said. Is it always going to put a ring, whether if there's a ring in the image or not? And the answer is yeah. This model is always going to place a ring down. So according to that detectability criteria I put down, I would not claim this detection.
So is any fixed flux leakage fraction assumed in these models?
No.
So n equals 0 to 1?
No, you let the flux fraction be anything you want.
Any-
Yeah.
The model is 2 rings.
It's one ring and a raster, so like an image. So there's a thin ring. So this is in the idea is you have a thin ring component to kind of model n equals 1, and then a raster to soak up the accretion flow stuff that can be quite complicated.
Maybe you'll get to this in a second, but have you considered 3 component model, a thin ring, a thicker ring, and then a raster?
I've done that. It doesn't fix it.
Okay.
I have tried that. I also thought of something like that as, yeah, it doesn't solve that problem. It's not in this talk, but yeah, I was hoping the same thing, that the thick ring would focus on n equals 0 and then the raster would soak up anything else, but it ended up just being this degenerate kind of mess.
Do you think it always goes, even when you have a thick ring, it goes to the thin ring?
Even when you have the thick ring and when you have the thin ring, I think the thin ring kind of just soaks up some weird, maybe a high frequency accretion flow thing, or some average between the n equals 1 and maybe like the n equals 0 turbulent structure or something that's leaking out onto those longer baselines.
I see.
Okay, so the last thing we wanted to check was, this is still, I would consider inconclusive with what the model, this thin ring radius is actually measuring. Is it n equals 0 or is it n equals 1? So to check this, we did a fourth model where what I did was I took this decomposition, shrunk n equals 1 by 20%, and then restacked the images together. So you get this n equals 0 plus n equals 1 shrunk ring. And then I wanted to see, where does this black dashed line go? And what you can see is the posterior does shift down a little bit for what it thinks the thin ring is, but it doesn't shift down by nearly enough. And there's still this massive separation. And so what this means is that this radius isn't, what we took this as is this radius isn't actually tracking n equals 1 uniquely. It's tracking some combination of n equals 0 and n equals 1. So claiming that this is a reliable estimator of the mass or of the n equals 1 properties is probably not accurate. It may be in a certain regime, maybe in a certain accretion flow style or something, but I wouldn't say agnostic a priori. It's going to be a reliable estimator.
One more question. These are all time averaged.
These ones are not. These are a snapshot. So I'm showing a snapshot image here. I've also done this for time average. It doesn't change it. But
If you were to do it for like as a movie, then you would see the n equal to 0 moving around, so the n equal to 1 would still be at a
Yeah.
location. Could you extract something? From
yeah, you could try something like that to try to use. I think that's a good strategy as well, is to try to use temporal variability to try to break this and see if n equals 1 is more stable or whatever. I would say just like from a snapshot perspective, I don't trust it on a single snapshot, but maybe after you average over a ton. The only thing against that is that when I do try time average GRMHD, it also doesn't work. You see this, it's basically identical to just the snapshot.
Basically, you would do it for some time, and you could probably for that model get something like an alpha 1 calibration for this sort of thing, where you get photon ring
Yeah.
equal to 1 and then just saying.
Yeah, I totally agree. You could do some calibration effect and try to suck this out. And I actually think this hybrid imaging approach is probably, I bet you could get better masked posteriors using this approach and what we did in the M87 methods. You know, I would just not interpret it as a photon ring. Okay, so what I think the implications for me, at least personally for me, is that I would not say that the hybrid imaging is a useful tool for detecting n equals 1 photon rings, or maybe even really measuring its property. it always puts a ring down, and it doesn't reliably seem to extract the n=1 properties. So then a question becomes, I'm also a member of the NGEHT. It's also a great telescope. I love it. Just had a meeting on it last week. So the question is does the NGEHT fix this? And the reason you might start to look at this a little bit is that, once you take in 345 gigahertz, you get quite a bit longer baselines, and the ratio discrepancy between the n=0 and n=1 contribution kind of start to become on equal footing, or maybe even n=1 can start to dominate for certain snapshots or whatever. So maybe what's happening here is we just didn't have enough power and long baselines for the model to actually key in on what we wanted it to do. And so the next thing we did was we took the NGEHT data set and did the same type thing. So we had a thin ring model, a thick ring model, and we, as well as this raster to soak it up. And what we found was that the ring diameter just focused on the peak emission of n=0. So it did exactly the opposite of what we were hoping. This extra baseline power didn't help us. It just put a ring component at the peak of n=0, which is significant. And because the NGEHT is such a precise instrument, at least compared to the EHT, you can actually see the separation. You actually see this large offset here. And once you put a thick ring down, it's measuring some thickness. It's probably some thickness of the GRMHD once you blur it with a kernel or something like that. I bet it would, at least in a profile image, that's what it looks like. It's just matching the GRMHD profile extremely well. And then the ring flux is still substantially biased. So I would say at this point, the NGEHT doesn't save us from this problem. Hybrid imaging is still giving a pretty biased result. And then you kind of see what it's doing here in the, like I said, these profile plots. So EHT is shown in this kind of yellow, NGEHT is shown in this kind of green. And what you can kind of see here is that the this thin ring width, it's a little too big. It's not really lining up with this little peak here. The profile actually doesn't look too bad of the green one. And you can really see this on when we actually fit the thickness of the ring. The green line is really following this blue line quite well. The center region is really hard. It's a huge dynamic range. You're going to just struggle with this no matter what. This is quite a deep shadow. But at least for the overall profile, I actually think the model is doing a really good job. It's just ignoring these little bumps here because it doesn't really have power to see it. So what does this imply for the NGEHT and hybrid imaging? I think the current incantation of hybrid imaging appears to fail for both the EHT and NGEHT. Say the ring properties are not accurately recovered. I wouldn't trust them. I wouldn't claim you could make a detection. Other tests we've done, I can show some slides on this, show that if you use a perfect geometric model, it does work. But so what this means is that if you have the perfect model, you can extract it. We will never have the perfect model. I will never know exactly what the accretion flow turbulent structure looks like. I will never know exactly what's going around the black hole. So, maybe some extremely ingenious postdoc or a PhD student or someone else can figure out a really good model that works this. I think we're lacking that right now. And so maybe a better model saves us from this. The model that builds in more physics or makes more assumptions can be a more reliable estimator for n=1, but I don't think we have that right now.
So I want to ask a question here, and with recommending Prashant was saying the n=0 ring is probably going to be much more susceptible to time variability.
Yeah.
And the n=0 ring, I think, will exhibit a lot more spectral evolution.
Yeah.
So is it perhaps more prudent to say that more work is needed on algorithms, which might incorporate snapshots over time?
Yeah.
And then it might look at multi-frequency synthesis imaging, where of course, the n=1 ring should be extremely achromatic.
Yeah.
Whereas the n=0 ring may begin to exhibit spectral tendencies. Maybe we're just not there yet.
I think that's
subtly suggesting.
I hear you, Chef. I think it's a great suggestion. I would say maybe building in these other physics into the model will help us a lot in measuring its properties. Whether that claims a detection at that point is a different beast, because we're folding in, I would say we're being less agnostic at that point. Once we're building in more and more properties of the photon ring into our model, whether you want to claim a detection or not, maybe I think there's a good discussion to be had for that. But I think I tried to give me a way out here. Better models or priors exist. So it is possible that a better model or a better prior exists and solves these problems. I would say the current incantation is untrustworthy.
I think I'm sorry, can I just say one more thing, just to follow up? I do feel I should point out, and maybe this is for after the talk, that when we were proposing for the EHT, you would have been very surprised to see the rudimentary nature of the simulations we did to show what we thought was possible. And it wasn't until really after we had some of the data that we've gone through some of the imaging challenges and refinements of the technique that led us to believe in the robustness of the result. So sometimes one has to be a little bit aspirational.
Oh yeah,
I
I think that's
not close the door a priori.
yes, that sounds good. Oh
Just amusing.
yeah, sounds good.
I was curious, so if you go back to your last plot, right, so is there sort of an optimal ring thickness for any given instrumental configuration?
So what do you mean by that? Sorry.
The fact that, are there inherently ring thicknesses that just going to be not reliably measurable at all?
Yeah, I would say
Whereas-
I would say there probably is something, and it's probably just related to the longest baseline you have. There's going to be a longest baseline that provides a minimum scale.
It'd
could-
still be that, it will still be the instrumental. I was
Yeah.
wondering if this would fold in another
It is,
limit, right?
I think, if you put in more physics, that you might get out to like a thinner, like no, technically the EHD is like 25 microarc seconds. We can reliably measure a ring of, I think that's thinner than 25
Right.
microarc seconds with some reasonable.
With better physics.
Better physics, better model or whatever. I think this is not, a factor of twiddle 2, this is 10. You're trying to go from an instrument that's 25 microarc seconds down to a feature that's microarc second in width. That's a lot to ask an instrument to. I think VLBI astronomers, when they hear super resolution, their eyes glaze over and they think this is unreliable, don't do this. And then that's, I think, going from like 25 to like 15 microarc seconds, going from 25 to 1 may make them a little angrier, but I don't know. I think, if you come up with a method that shows and solves all these problems I put up, I will believe it. I just don't think we have it. Okay, so the last thing I kind of wanted to talk about is, I think there's been a little talk about moving to space. So this is EHT plus an orbiter at GEO. So this is like the Event Horizon Explorer concept. There's a few different ones. You could put one at LEO, GEO, maybe an Earth Moon system. I'm going to look particularly at some like GEO thing. This is like a rough limit for what you would expect at GEO. And the nice thing here is with this time average GMHD simulation, you can see there's this. We're not in this place where they're on equal footing. There is a clear separation between what n equals 1 is giving you and what n equals 0 is giving you.
Right. What is geostationary?
Geostationary orbit. So
Okay.
satellite that's orbiting at the same period as.
I've been taught
Okay.
by the gurus of orbital dynamics to say geosynchronous. Rather than geostationary. Geosynchronous can go radially,
Okay,
can shift a bit, but stays on sky at the same place.
okay,
Geostationary are like highly coveted. You can't possibly get a space there.
Okay.
Because the military wants it, communication wants it. It's like all spoken.
excellent. All right.
So geosynchronous is also-
Along with the parking space and hardware.
I think geosynchronous orbit, there's also the sort of more general condition where they're not necessarily locked at a particular sky position all day. They just pass over that point repeatedly, right? Because they have the same period, but they could be tilted forever.
Yeah.
It's like long-term parking as opposed to.
Yeah, exactly.
Playing by your turn.
Where you're covered.
Yes. Yes, thank you. I will make sure I'm more specific about the orbit. So The specific orbiter we picked, you know, I think like Daniel said, you can pick a few different inclinations for what the orbit looks like. This is a very particular one. So it looks like a circle. So there's just this big region that the orbiter kind of goes along. I'm also going to assume an SCFD of 10,000. That's like about a 5-meter dish. Maybe a little optimistic for what we can put in space, but gotta start somewhere. So I'm also only going to focus on 230 gigahertz, 345 detections may be pretty difficult when you're talking about a 345 to
It's too
EHT
bad we
2018.
can't CubeSat it, right?
Sorry?
It's too bad we can't CubeSat it.
Yeah,
We
exactly.
just launch it tomorrow.
I was thinking befriend Elon Musk and put a little radio dish on all of his Starlink satellites. Make it lesser. But it means I have to interact with Elon Musk.
It's on the internet, just. so you know.
Oh no. Don't come for me. Please. And my inbox is gonna explode tonight.
We have fun here.
So I'm gonna start with a time average GRMHD simulation here, just for simplicity. And what you find in this case is here I fit one of these hybrid models again. Here I do a trick. Shep said, why don't you fit 2 rings in a raster? That's what I do here. Fit 2 rings in a raster. I don't force the one ring to be thin. I fit 2 rings. Both rings thickness can be anything they want. The only restriction I make is that the second ring is thinner than the first. This is not an actual restriction. It's just to prevent a trivial degeneracy. And what you see here is that, at least visually, it looks like the profile of the reconstruction and the truth actually match really well. They seem to have the same peak at the same location. The overall structure looks really good. And visually, you know, if you did your imaging algorithm and out popped this, you'd be pretty dang pleased, I think, and excited. And quantitatively, what you actually find is that it does fantastic. It gets the diameter perfect. It even makes a pretty decent estimate of what the ring width is. It does about a 1% constraint on the ellipticity, nails the fractional flux, even gets the shift from for the shift that you get from n equals 0 and n equals 1. So it does really well. So now we just need to build an orbiter, right? There's a slight problem. What happens when you add turbulence or the n equals 0 type emission? And the reason this is important is here, you know, I see clean separation between n equals 1 and n equals 0. Now I add all this substructure, and this separation is not so clean. We're back into a regime with these geo baselines where this high frequency structure from the turbulence is kind of bleeding in to the total visibilities here. And so you might be a little worried that we're going to be in a regime where we're going to struggle again. And it turns out that's, yeah.
The central is the NGEH2?
Geo, sorry. EHT, NGEHT, Geo. I should have put a little arrow.
But the central part where it's green says NGEH2.
No, it's a label. There should be an arrow here. So EHT limit, everything inside.
It's always to the left of the line.
Yeah, exactly. Yeah. So EHT limit, boom, NGEHT limit, Geo.
I see limit. Got it.
Yeah, sorry.
So
Oh,
what's the final one? On the right.
beyond. Moon, L2, Alma in space, whatever you want. I leave that to
The reader.
the reader and the funding agency.
The imagination of the reader.
Exactly. Yes, whatever they're willing to give us money for. So what it turns out is all that high frequency structure does start to create a problem. You can see it immediately in the reconstruction. Something bad is happening here. These ring components are kind of just like aliasing off each other. And these parameters that we're extracting are all extremely off. So you see the width, again, we're at this place where it's super biased, the displacement's off, the flux is off, the ellipticity is off. So you're not, I would say, accurately recovering n equals 1. And so at this point, I think there's a few ways out here. The nice thing about geosynchronous orbits is maybe we could stack over time, add visibilities over time. We're going to have very similar baseline coverage day to day. So maybe we can coherently average visibilities. This requires us having extra really good calibration. But, you know, optimism. We could also try to build in a model that does something like Shep said, where we try to fold in some achromaticity of the photon ring or some time stability of the photon ring into the model, maybe over multiple observations. That's a way out as well. But I think at this point, this is very preliminary. I don't have a good model for this, but I don't think the orbiter is going to be launched in the next year. So we got some time to think about this, a lot of time.
Can I ask my question?
Yeah.
Everybody wants to know this. What's the advantage of geosynchronous orbit? Why is not exposing it along this process?
So a low Earth orbit is fine. You just don't get as long. You don't get as we really want baseline length. So you'll want something with like a lot of length. The other thing that's nice about a geosynchronous orbit is downlink's not quite as bad than if you put something way out there. You have to figure out how to get the data from the telescope to Earth. And that's really hard. Geosynchronous isn't too bad. Low Earth is better, but it doesn't get you that baseline length that we're really after.
So just one dish on the moon is not.
Yeah, I don't think a dish on the moon is probably you're gonna get you don't just want like one baseline in one direction
Right.
just sitting
You want
there.
it Populated.
You'll want to at least have like a closure phase or something, or some like maybe like moon and something on the opposite side of moon, or some like two orbiter. You'll want something like that, but a single station is probably not great for these types of experiments. There's things that can mimic photon rings in a single direction. You would want, I would think, at least two directions to stick to get this.
And also the flux density decreases.
And the flux density decreases. Yeah, if you, no, it's fine. We'll put a 20-meter dish in space, Chef. 100-meter, and we'll integrate till quantum limit.
Now you're just teasing.
Yeah, we all do that.
The thing about low Earth orbit is it's a couple of 100 miles up, so it's smaller than separation between telescopes on the Earth. The thing that you get for other purposes, not this, is, you get it goes around every 90 minutes or whatever it is. And so you can fill in the UV plane in a nice way. So for certain purposes,
Great.
it's great. It would be a big help, but not for this. This, we need something that's several times Earth, the Earth separation is impossible for it to be worthwhile. Otherwise, going up to the space station is like going from New York to Boston. It's not much.
Okay, so it doesn't have to be geostationary, it's supposed to be somewhere in this.
Okay, so that's like the end of it. That's my summary. Is basically, I think, at least current incantation of hybrid imaging, maybe we can build in more physics, is not able to accurately measure the properties of the n=1 photon ring for the EHT and NGHT. Currently, hybrid imaging also always gives a photon ring, whether it's there in the image or not. Whether that's of a deep fundamental concern to you is up to the beholder. I think that's a good discussion for like HPC kind of thing, what they think a good detection criterion is. I think it's a really interesting question that deserves a lot of thought. The other thing is that moving to space seems to help a lot. All that extra scale, probing all those fine scales seems to really help. So I think space is very interesting for this. I don't think the thing I brought up with the accretion turbulence being the accretion turbulence causing a problem is insurmountable. I think it's something that can probably be fixed with more dedicated time. These results were done very quick. So I think there's a lot of work left to be done there, and I don't think it's like dead in the water. One thing we still lack, I think, even with this, is one of the really nice things about LIGO or CERN, like Higgs thing, is like they had like a criteria. This kind of goes to detection. We're looking for a bump, 5 sigma. Great, we'll claim a detection. We don't have this like yes, no type thing in any of our modeling yet. I can fit something to it. I can get a posterior. I can say some stuff off of it, but it's not like a little flag goes up and goes bing, bing, bing. We got it. It could be, I think we're still pretty much lacking what we're going to use to claim a strong detection criteria. All right, that's everything.
Got a couple of minutes for questions.
You have a bullet that says, what about polarization?
This was for you, Daniel.
I know.
Polarization will save us. Yes.
Well, yeah, I do think polarization will save us. I don't think it saves us at the NGHD baselines, importantly, at least not at 245. But if you want to hear more about that, go to my ITC talk in a few weeks, but we'll see. Anyway, but yeah, I do think there's hope for protections, but it is so tricky once we're just trying to do it with Stokes eye and the image domain.
Exactly.
I think I would just generally say, I think the big unknowns that are preventing us from making wild claims here are mostly on the accretion physics side.
Yeah.
That we don't really know what the heck these things look like in the way that we trust. And we need to make huge assumptions in the accretion, like assuming GR to me is weak.
Yeah.
Right, it's assuming things about the emission geometry and magnetic field geometry that scares me. But anyway, all of this work you're doing is incredible. So that's why I just wanted to see you now.
I completely agree. Everything.
His name is Daniel Polarization.
Yeah, exactly. Daniel P for polarization.
Good luck.
So, just on that, and also what we're ending with, so what you were saying is there's no clear criterion for laser detection, right? So this sounds to me like we need a null test of,
Yeah, exactly.
and that's something that we're working towards. And, this is definitely possible. So what we could do, this is something that we're doing with, Dominic and, Michael.
Mhm.
We're trying to, fix a curve and, vary over the accretion, morphology.
Yeah.
And then get maximum limits on how large the filter ring can change
Mhm.
with size, everything.
Okay.
And that will give us this is just tracing now.
Yeah.
Doesn't have anything to do with emission physics at all. So it'll give you a maximum bound on the n equal to 1 ring for curve period.
Okay.
So if you're within that, then great. Yeah, like your detection matches your null test.
Yeah.
If not, then you're problem, then it's a problem.
Yeah,
So
okay.
you can have some sort of tests like that.
Yeah.
That's a comment. Previously you were showing earlier on that you scaled down the ring of the n equal to 1 and you were trying to see to get, and there was a test. If you had non-current models, non-current GRMHD models, would you then be able to make statements without scaling things down and saying that, I'm getting the ring right, the n equal to 1 ring right? Because it sounds to me like to model non-currentness, you're scaling the n equal to 1 ring down arbitrarily.
Yeah.
But if you use actual geometry models and try to do this, and you get the n equal to 1 ring right for curve and non-curve, then that'd be a good test. Right?
Yeah, I agree. Yeah. Yeah. If you change I think, yeah, something like that where you put in some alternative metric or theory and something and see the ring change and you see it change as well. That's a good test as well.
So I guess I wanted to push back a little bit on the idea that a detection needs to not be making assumptions.
Okay, yeah, that's
Right.
fair. Yeah.
Because if you're comparing it to something like LIGO, where they are using templates in order to make the detection, obviously there's a lot of assumption being built in there. And so it seems like some of the other things that you were saying about criteria for detection are more important, like whether a button ruled out false positives, for example, and it sounds like really the biggest difference here between like the LIGO templates and the fitting with models that you're doing is the fact that sort of the noise here being the sort of n equals 0.
Yeah.
Is correlated with the ring to a degree that it's hard to separate.
Yeah.
Whereas if you're using templates where the noise is, we pretend it's Gaussian,
Yeah.
then you can separate it out nicely. But I think that, making assumptions about accretion, yes, it's scary. But if you could demonstrate
Yeah.
that you're not at risk of false positives, then I think maybe that's not something to worry about. So I guess I just would say that maybe the emphasis needs to be getting too worried about making assumptions. I think every experiment makes assumptions.
Yeah, I think I was probably a little too strong on that. I am a Bayesian person through and through. You always make assumptions, you always make hypotheses. I think I am beholder of what those assumptions are and how strong those are important, but I agree. If you come up with a method, you do all these tests, you show it's predictive, I'm like, all right, we're good, I think.
And the nice thing here is that you can really do the tests with the truth.
Exactly.
See what happens. That to me at least is very convincing that if you can show that works.
Yeah, I think if you can show a method works in all GRMHD simulations, that's super, super useful. I hear distant echoes of people being like, but their GRMHD simulations, how good are they? But I think it's a really good start. And if you show it, I'm pretty confident.
So I think it's time for
So one
colloquium.
last thing, so everyone's waiting to get in there, but we have talked all about the possibility of even higher frequency ground observations too.
Yeah, I think,
There are some sites where we could go to 450,
yeah, I think
even 690.
we've even done AHA with 1 terahertz.
So I don't want to.
So Eric, we're gonna have to,
Well, I-
after.
Six nine does.
Thank you to everybody on.
Photometric, this one fits. So if we can go to 6.9, let's start that one. No, I think we should do something.
Yeah, I
Just talk about it.
I agree. I was under the assumption that the NGHT stops at 345.
You
But-
stop at nothing.
We stop at nothing. Let's do 2 terahertz. There's a window.
Yeah, I think we figured out.